Hey folks, I'm Saptarshi Mukherjee. I'm a software engineer 3 at Google and I have been a computer programmer for quite a long time. So in this playlist we are discussing the problems and solution approaches and solutions of Leetcode weekly contest 385, and this is the second question, second problem of that contest. So let us see how we can solve this. What we are given is two positive integer arrays, ARR1, ARR2, and then there is some prefix idea. Common prefix of two integers is an integer c, such that c is a prefix of both. Fine. We need to find the length of the longest common prefix between all pairs of integers x, y, such that x belongs to ARR1, y belongs to ARR2. So this is the main line. This basically says we need to find the longest common prefix between all pairs of integers x, y, such that x is in ARR1, y is in ARR2. Length of the longest common prefix among all pairs. So if we look at one example, 1, 10, 100, and this is 1000. So we have to look at a pair of one element in ARR1, one element in ARR2. So if you look at this 1 and 1000, that is what they have done here. 1 and 1000 has a prefix of length 1. 1 is that prefix. So this is the longest. Then they have taken 10 over here and 1000 over here. So it's 10, 1000, where the longest is 10, 10. Similarly for 100 and 1000 it's 100. So for here, between 1 and 4, there is no common prefix. Between 2 and 4, also no common prefix. Between 3 and 4, also no common prefix. So, no match. If I take another example, let's say this is the example 1, 10, 100. Say if I look over here, between 1 and 1000, there is a match of 1. Similarly, between 1 and 104, there is a match of 1, and so on. If we look at the other examples, so let's say between 10 and 104, we have 10 as the prefix. And if we look at 100 and this 1000, we have 100 as the prefix. I'm not showing all of them, but these are the pairs possible. If I take 10 and 104, then 10 is my prefix. If I take 100 and 1000, then 100 is my prefix. So in this way, we can take multiple pairs and we can see which gives us the longest one. And now the question is, how can we solve it? So one is we can have a basic approach. We can say, hey, if I have one integer from left, another integer from right, I can iterate both of them from left to right in a string manner, like iterating in a string. You can iterate digit wise in both of them and see, okay, how much is matching. So what's the time complexity? Let us see if we match them one by one. So there are these many integers in each array, 5 into 10 to the power 4. And each element can be up to 10 to the power 8, which means these are 8 digits long. They are maximum 8 digits long. So comparing digits by digit by digit is fine. There are only 8 digits. So I can say this is just 8 operations. But I need to do for how many? These are the lengths of my array. Both go up to 5 into 10 to the power 4. So basically, if I say these are my x1, x2, x3 in my first array up to xn, and these are the elements in the second array up to ym, then what is the number of pairs? I have to look at every xy. So basically my number of pairs will be the number of x multiplied by number of y, which basically gives us 5 into 10 to the power 4 multiplied by 5 into 10 to the power 4. That's the possible number of pairs. So it's basically 25 into 10 to the power 8, which is more than 10 to the power 8. 10 to the power 8 is basically the upper cap on the number of operations that we want to allow. So definitely this will give us a TLE verdict. This will exceed the time limit, TLE. So now the question arises, how then can we solve it? How can we solve it better? What can be a better way of solving it? So what is the, whenever I face this question, okay, what is the best or what can be a better way of solving it, I try to find what is bad with my algorithm. Where am I taking time? So over here I'm basically taking time at this position, that I'm checking, I have to check 1 separately with each of them. I have to check 10 separately with each of them. I have to check 100 separately with each of them. Can there be a way so that I can check any of these numbers with all of them together. How can I raise this kind of assumption? From my experience of these pattern matching things. Whenever we have some pattern matching things, when we have to match a lot of strings, then we try to compose them, we try to uh, bring them in a data structure such that multiple comparison can happen together. So here we need multiple comparison, we need so many xi's to be compared, xy's to be compared, but again the xy's are many in number, so we have to parallelize in some way. And so, a best way or a very common way, whenever pattern matching comes to the question, a very common way of optimizing it is basically to store the strings that we want to compare a string against in a certain data structure known as a trie. So we say that store all the strings in a trie. So what do we want to do is something like this, that all the ARR2 elements, if we can store in a certain trie, then for each x that is a part of ARR1, we can query that in this trie that, hey, is x, or what is the prefix of x? What is the maximum prefix of x in that trie which contains ARR2? So I repeat, in trie we will store all the words of ARR2, and then with every word in ARR1 we'll ask, hey, if I want to find out your maximum match with the ARR2 words, we only need the max. So can we say, okay, search in all of them together? You don't need the individual results, you just need the maximum. So over here, let's say, if I apply this idea on this given, or on this particular example that we have taken, 1125, 104. This is my ARR2, 1125, 104. So how will it look like? It looks like something like this. That initially, let's say I'm over here. That is my root. I'm starting over here. Then with 1, I'm basically going over here. Then with 0, I'm going over here. Then with 0, I'm going over here. Now, I want to now come to 125. So 1, fine, it's the same thing, starting with 1. And then I'm coming to 2. For 2, I'll have something. And then for 5, I'll have something. Then 104. So I'll come to 1. From the root I'll come to 1. Then I'll come to 0. Then from here I'll come to 4. 4 from here will be a separate node. So by this what happens? Now if I want to search a number, let's say 100. Let's say I want to search 100. What can I do? I'll say, okay, start from here. 1. Do we have 1? Yes, we have 1. So go along the 1. We are going along this one. Now we will ask, okay, do we have 0? We'll say, yes, we have 0 along this. So we will go through the 0. Then we'll ask, hey, do we have another 0? Yes, we'll go along this. So we have another 0. We'll come over here. For 1000, I think I missed storing the entire 1000. So 1 0 0 0, 3 zeros. So this is the second 0. After the second 0, there is another 1. There is another 1 0 due to that 1000. So when I'm trying for this 100, I'm reaching over here. This is my 100. If I try for something, let's say 126, then let us see for 126. For 1, I will say, yes, go to 1. From the root, there is something by 1. So we have gone to this 1. Then we will say, okay, after this, I need 2. So, okay, take 2. Take the path to 2. This is the node. So everything that starts with 1, 2 lies over there. I'll go there and then I'll see what is the maximum I can go. Then I want 6. From here, there is nothing like 6. There is nothing like 6. So I'll say stop over here. This is the maximum prefix you have. So 1, 2 is the maximum prefix you have. Now, I'm not comparing this 100 or this 126 with each of these separately. That would have costed me a lot more. I am rather storing all of these together so that now when I want to check for 126, I can go step by step. I can just go digit by digit. At every digit, I have one traversal to make. I don't have to check against so many strings. That is the beauty of a trie. So a trie basically says that whenever you are interested in the prefix or the suffix, store in that manner, start storing in that manner, digit wise, character wise, whatever, so that those strings which share a common prefix will come together at the beginning, so that when you are then querying by some prefix, you will come down there and you will see that you basically are you're including all those strings under you. So it's something like this, that let's say we are starting a number by 1. We are asking that, hey, how many numbers start with 1 in this array? We can sort of come down to this 1, and within 1, however many numbers are saved, these leaves of this tree-like structure indicates that how many numbers have been stored. I'm not going into some corner cases of one of them being a prefix of the other, all those things. But basically, I can say that this, when I come over here, now I have access to all these numbers. I can go to whichever one has the biggest match for me. I can go along that path. So yes, for longest match, we can use this. For number of matches of that prefix also, this can be used. We have to maintain a count. But for this simple implementation where I just want the length, if I just want the length, what will I say? I'll say that, yeah, store all those numbers, store all these numbers in this trie, and then for each number in the other array, just keep on going down up to wherever you can go. So if you can go up 3 steps down, then 3 is your answer. If you can go 2 steps down, then 2 is your answer. So for whichever x or whichever element of the other array, you can go to the maximum depth. That is your answer. The others by default are null, so I will not populate them. I will say yes. We'll look at the implementation. You can actually study this implementation from a number of websites. Trie is a very widely used data structure, and I had given a lecture on tries. You can actually take a look at that. I've shared the link in the video. And discussed how these character tries and binary tries can be used. It's more linked to the character tries. You can see how you can implement them, solve them. Okay, so that's it. Now let us look at the implementation over here, how we are implementing this. So these are two very common functions which you will need. So what am I doing here? I'm basically saying I'm inserting a word into the trie. I'm inserting this word key into the trie. And longest common, I'm basically finding, for a certain key, I'm finding what is the longest common. So this is the first part where I'm populating the trie, where I'm adding the strings into the trie. And this is the second part where I'm finding for a given query string that what is the common, the longest common, largest common. This is my simple node. What am I storing here? I'm basically storing, okay, this node contains the links to its children. It contains links to its children. Why 10? Because from 0 to 9, there are 10 digits. So I'm basically storing those links. So basically, if you look at from here, you can go to 0 to 1 to 2 to 2, 3, 4, 5, 6 up to 9. So I'm basically storing them as links. So this guy will contain an array where 0 points to this and 2 points to this. So each one I can store as an array, and whichever ones are not populated, wherever I don't have nodes, for example this one I don't have, I'll keep that as null. I won't touch that. So I'm not initializing everything as valid node. I'm keeping them initially as null. That is in my constructor. I just form the spaces. Next, let us look at this. What am I doing? Finding the lengths. And then this is my root. The root contains 10 children. All of them are null for now, but it just has the reference for 10 children. We can add that. Then we are saying insert into trie. We are converting this number into a string. So we are populating with the first array, ARR1, and we are querying with the second array. You can do the reverse also. So with ARR1, each number will be added to the root. How? Let us look at this. We will iterate through this number, through this string you can say, and if it is null, then we will say, okay, that means no other number existed with this prefix till now. So add a new thing over there because this is a valid number. So basically we are adding something and then we are going to go over there. This is basic trie implementation. You can look it up in more detail. I'm going to the children one by one. So what does this look like? From here, if I say go to the child, it will go there. From here, if I say go to the child at 0, it will go there. If I say go to the child at 2, it will go there. This is how it will move. So children at 2 will take me from here to here. This is what I'm doing. So I'm basically checking, hey, do you have something at that location? If you don't have anything, then please add something and then go over there. Why go over there? Because from there we will traverse more. We will keep on forming that layer by layer. So we are basically going down that layer while inserting it. While finding it, we will just check whether it's there or not. If it is there, if it is not there, if nothing is there, that means up to here you have to return. That okay, the match is up to here. And if you see something else is there, this is not null. If this is not null, then you will go down. You will say, okay, reach up to the bottommost point. If you come out of the loop, that means you have the entire string as a part of that, which means the length of the string is your answer for this particular key. So for every key, we are checking that for every ARR to J, we are checking that, hey, is this sharing some prefix? What is that longest prefix? We are finding this for every ARR to J, and whatever answer we are getting for every ARR to J, we are finding the maximum of that with the len. Final len is our maximum answer. So that is it. This is a very good problem on tries. For those of you who are beginner kind of programmers and want to explore these good data structures, this is a good problem to give you some interest, enthusiasm in trying out these good data structures, because these are easy problems on tries. So look at the video that I had linked in between, and if you want to learn a bit about tries, you can also study at some other places, and then you can try solving this problem, because this will give you some confidence on how you can solve problems using these data structures tries. Over here, I've just stored the children. Sometimes we store some other information as well, like up to here, how many strings have visited. Here we don't need that information, so I'm not storing it. You can store a count, that how many strings have visited this path, or you can store whether a string is ending at this position. You can store some boolean variable over here. For every node, you can store that boolean variable. You will find some of those examples in popular interview questions, as well as in that lecture that I had taken, whose link I had shared. So yeah, that's it. Try solving this problem and let me know if you have any doubts. Take care, keep coding. Do like, share and subscribe if you find the video informative. Do share with all your friends who might find this informative. Thank you. See you.